Okay, we're going to talk about magnetic forces on moving charges, section 29.7 in your book. Now, Ampere, he had Ampere's law, but from Ampere's law we saw that current, we know, creates a magnetic field, but if you have moving charge, it acts like a magnet. Well, if a moving charge acts like a magnet, what if we have a magnetic field and we got charge that's moving? There's already a field there and charge is moving. There's already a field there. Moving charge acts like magnets running around. So this external field is going to push on that charge that's moving because it's acting like it looks like a magnet to this external field because it creates its own magnetic field there. So let's look at how a moving charge is affected by an external field. And we see, and it makes sense, that since you got two magnets interacting, because moving charges basically act like a little magnet, that this external field is going to push around this charge. And so let's see what's going on there. And it's not that simple because of, you know, how we did the dot product here. We had to have, if the magnetic field, you know, there's a perpendicular and parallelness into this, and it works the same way. And basically what Ampere found out was, if you have, let's say, a B field like this, this is your B field, and the velocity of the charge and your charge is moving, the velocity of your charge is in this direction. If B is parallel to the velocity of your charge, what happens? The magnetic force that you get, any force on it, any push, zero. There's no effect. There's no effect. Now, he found that if this is your magnetic field, external magnetic field, and your charge, velocity of your charge is in this direction. So if the B field is perpendicular to the velocity of your charge, found then that the magnetic force on that one, on that charge here, is maximized. Greatest effect. And of course, between zero, I'll say parallel and perpendicular, the magnetic force increased. And if you know a little bit about trig, and you're already thinking parallel, perpendicular, how did it did increase as a cosine function. Excuse me, that's sine because zero. Sine of 0 degrees is 0. Sine of 90, of course, is 1. It increases as a sine function. So it increases as a sine function. And he also found that, I'll put this right here, if the magnitude of the charge increased, magnitude of the charge increased, then the magnetic force increased proportionately. It increased proportionally. When you got twice as much charge, you got twice as much magnetic force. Well, from all of that, we've got a sine function here. You could say that then Q, the charge, the amount of charge Q, the magnitude of the velocity of the charge, and the B field. Of course, B field is twice as strong, twice as much magnetic force. If the velocity of it is twice as much magnetic force, that's going to be magnetic force. But it was mediated by direction. In other words, direction, it's affected by how much direction. And it's a functional sine of the angle theta, where theta is the angle between the velocity vector and the B field. Okay. Now, we can write it in terms of magnitude, or if we want to get fancy. We like to get fancy. Physicists can be pretentious a little bit mathematically. They like to be fancy math. So we can write this as QV cross B, where this is a cross product, a vector cross product. We did this a little bit with torque last semester. If you don't remember, look it up, Google it, DuckDuckGo it. I don't care what you use to look it up. But you understand dot products and cross products. You get this in Calc 2, Calc 3, maybe one of those. We're going to, again, try to be smart about it and do zeros and 90 degrees, maximized or minimized. And if we do that, it makes our mathematics a lot easier in this level. But of course, you know, you can get to the next level. We'll take that into account. You have to do determinants and all that other stuff. We're not going to get into that here. But that's the basic understanding of it. And this is how it operates. All right. Now, you can do this using what I call the physics gang symbol. Dude, I can stack them. Stack them. I can do this. Yo. I can do these sort of things. But my physics gang symbol, which is my cross product, right? Vector cross product. You know, dot product's simple. That was the old gangs that, you know, we took care of those guys. We got to do this. We got to do this. And what you got to look at it as is you use your thumb is the velocity vector. Okay? Your second finger is the magnetic field. So here, if the thumb is this way, the magnetic field is this way, and then your middle finger, the one that where you guys hopefully don't tell me I'm number one, that one is the magnetic force. So those are perpendicular, and both of these are perpendicular to the magnetic field there. So you got your thumb, your middle finger, your B field. Velocity, notice velocity, magnetic field, here. Thumb, second finger, middle finger. And you can do this, and you can find, now you can do it like this if you want. It's called a curl. I'm not going to introduce it like that. But you can do it as such. Velocity, magnetic field here. So let's assume in a case where the velocity is this direction and our magnetic field is into the board. So what would be the direction of the force on some charged particle, Q, let's say? So some positive charge here. Those are all the magnetic fields. Here's my little positive charge going across this way. Okay? And that's a vector. So thumb into this. So the force on this would be the force that on this charged particle is straight up. The force would be straight up. Velocity across, B field into the board, magnetic field straight up. Yeah, got this. All right. Questions? this a little bit more. Y'all are just physics dogs as we do this, right? Now, if at this point, let's use the same situation. So we got our B field into the board. Here, there's my charge. At this point, it's going this way. But there's a force on it in this direction. Well, if I'm going this way, I got to force up. I'm going to have to start turning it up a little bit. Turn it up, you know, and everything. I'll be going upwards some. So my path on it, let me get where's my orange? I had an orange. Ooh, you black. Okay, so the path would be like this. Now what about here? Now I got my charge. At this point, my velocity vector is this way. B field into the board. Force is now to the left. To the left, to the left. I'm sorry. Kelsey, I know can do the electric slide. So now here's my magnetic force. So now I'm going this way. I start going back the other way. So now I'm going to start going. I'm getting pushed in this direction. Right here, my velocity vector is in this direction. Velocity this direction. Now the B field is into the board. Now the force is down. Right there. So now I've got a magnetic force going down. Dang it, this starts to look like circular centripetal motion. So it's going. And right here, velocity is in this direction. The B velocity is in this direction. B field's into the board. Now my magnetic force is towards the center again. There's the direction of my magnetic force. And it's going to make a circle. So if I have a charge moving plane perpendicular to a magnetic field, a consistent, non-changing magnetic field like this, plane perpendicular means in this plane, its plane of motion is perpendicular to that field. It'll move in a circle. It will actually move in a circle. And this is known as cyclotron motion. And no, he's not one of the Autobots or Decepticons. But this cyclotron motion is moving around in circles. If he is, I guess he'd never do anything because he'd just be moving around in circles. Now, or he'd be singing like songs like "You Spin Me Right Round, Baby, Right Round." Even nobody here doesn't like that joke. So this is cyclotron motion caused by a charged particle moving plane perpendicular to a magnetic field. It's called cyclotron motion because what did we develop from this? Cyclotrons. So particle accelerators, because if you keep increasing the strength of the field, you can make this thing go faster. You can do with this. Also, mass spectrometers. And I'm going to do an example on this here in just a minute. Okay? So, questions? What? Nick? Okay. Yes, Nick, that's correct. Nick's, good job, Nick. Alright. So, let's look at this over here. No, MLA, that's not how you do it. But that's okay. And Melissa, quit telling me something about the middle finger part. That's not very nice. Now, one thing I did forget on cyclotron motion, what you can do with this, you can actually set this up, and as it moves around, you can say, well, this circular motion, which we know from last semester is mv squared over r, we know that's equal to, because here they're all perpendicular, so it's going to be charge, I know Kelsey, I'll change, QV times B, that cancels there, and you can actually get that cyclotron velocity, or the velocity of your particle moving, or your charge moving in this circle, in this magnetic field, is equal to QB, I'm sorry, they do radius. The radius of the motion. Radius of the motion is going to be equal to mv over qb. Of course, velocity, you can solve for velocity as well. That's how fast it would move. The radius is important because that's how big you need to build your cyclotrons. And then really, really big ones are needed because if you get it going really, really fast. So that's cyclotron, the radius of a cyclotron. Now this R, though, is important as well for a mass spectrometer. So let's assume, now this is example 2911. So what we're going to do, we're going to take 0 volts here and 500 volts on this one. It's a capacitor. Now here we're going to have a uniform magnetic field. And if we do this, it talks about in example 2911, an electron accelerated from rest to a potential difference of 500 volts. We're going to have an electron, so it's going to be a negative charge. And 0 to 500 volts. So remember, positive would go from 500 to 0. The electron's going to go negative, so it's going to come through here. It's going to get accelerated through there. So now you've got it coming out. The field, the electric field accelerates the charge, because this is basically a capacitor. And as it comes out of here, it's got a velocity. I'll put negative minus underneath. Now let's do our gain symbol, our physics gain symbol. Thumb here. Now normally that would be true, but since it's negative, we effectively have to switch the direction. We were doing that for positives earlier. Since it's negative, the force now isn't up, it would be down. So the magnetic force on this charge right here is going to be down at that point. So it's going to come out. And here, it's got a velocity in this direction. B field is still in. So here, here, there. It's around, remember it's negative, so it's going to be the other way. So I got to put my B field here. And basically, you're going to get, pow, it's going to hit the metal right there. Pow. So that electron's going to hit the metal right there. And it might make it glow. And if it hits, electrons hit things, you know, if there's a coating on it, old school TV says, it'll make them glow. It makes them because they provide a lot of energy to it. So the question is, what they're wanting to know is, what's this radius? What is this radius? Because this radius here, that would be 2 times that distance. 2 times that distance. Now, they decided to use conservation of energy to find it. And what they say is that, well, for kinetic energy initially, plus the potential energy initially, and then when it hits its basically got none of either one. This is initial. Say its initial kinetic energy, 1/2 mv sub I squared. That's its initial velocity. Or final velocity there. Final velocity. The magnitude will be the same. And they say that potential energy is just going to equal to Q times V. And if you remember potential energy, V is the electric potential. And we defined electric force as Q times electric field. We then defined the electric potential energy as Q times the electric potential, Q times V. Okay? I'm going to say that equals 0. Because they're going to basically be equal to each other. Alright? And let's find the velocity there. V final, so that's going to be 2. That goes over there, 2. And I'll move that, make that negative from the velocity final. Let's do it like this. V final squared minus Q times V. So V final equals the square root minus Q times V. And I got to put a 2 there over the mass of that electron. And if you plug in the numbers, since this electron, it would be a negative everything, that negative becomes a positive. And you'll get about 1.33 times 10 to the 7th meters per second. That is within a little bit less than 10% of the speed of light. So you're starting to get relativistic effects coming on there. Now, once you have that, now you can find the radius. Once you know this, you can find the radius. So now the radius is going to be equal to the mass of that electron times velocity of the electron from over there over the charge of an electron times the strength of the magnetic field in the problem. And once you plug that in this case, they give you the magnetic field. They actually calculate the magnetic field for it. They use the cyclotron frequency for it. And if I give you a problem like this, I'd probably give you that. I'm going to make you go into that in detail. But basically, they get that the radius is about 8.5 millimeters. Now, that's for an electron. Now, let's think about it. Say you had a proton. It's a lot heavier. Okay. And a proton is basically a hydrogen nucleus. So a hydrogen ion, that would be a lot less because of the mass. Now, in that situation, what you do, because this would get now less than a millimeter, what you do is you just really increase this voltage out of it if you can. And once you strengthen the, have either a weaker field or a stronger field here. And then, but what happens is, my apologies, since you have the weaker field, makes it go out more. But what basically you end up doing is, I said something wrong. If you have more mass, the radius would increase. So how do you keep that? Because it would go up by like about 1,000. So how do you get it to being so long? You increase the magnetic field. Okay. So what that basically you can do by increasing the magnetic field, you can use heavier molecules. So on whatever's getting ejected through there, you can actually know the mass of that molecule that gets injected through there. And if you heat up a material enough through an electric potential so it shoots ions out, you can actually determine the mass of the material that's getting shot out. Now, mass spectrometry, the spectrograph basically just separates wavelengths by position. This is separating mass of things by position. So further down the line you would go, the heavier it would be. The closer up here, the lighter it would be. So you can make a spectrograph, a distribution of mass as a function of distance. So you can use this to figure out what things are made of. This is how they work. This is how they work. Okay. Now, there's something called the Hall effect. Now, this is what we used in class, we tried to use, to measure magnetic fields. It's a weak effect. That's why, unless you get really, really good ones, it didn't work real well with what we're trying to do in class. And basically, I'll say this works inside conductors as well as in free space. So what does that mean? Well, say you have a piece of material here, and you've got some electrons, just going through here. This is some charge, and it's just moving in this. That's its velocity vector. Okay. And that's its velocity vector. And let's say you've got, here the magnetic field is out of the board. Just trying to keep it consistent with the book. Here the magnetic field is out of the board. So you got your positive charge carriers going through this way. So velocity out of the board, pushing it down. So it's pushing it down. Velocity, B field out.